This video will focus on applications of bases other than E. One of the most common ones is the compound interest formula. So if you have P dollars deposited in an account paying annual interest R, which is in decimal form, compounded N times per year, the balance at the end of T years can be found by the formula A equals P times 1 plus R over N to the NT power. There is a small typo there, NT. So if you are if you're depositing $750 into an account paying 5% annual interest compounded monthly, how much will be in the account at the end of 4 years? So my P here is $750. My R is 0.05. We're compounding monthly, so that is 12 times a year. And at the end of 4 years, we'll have T equal 4. So some words that you want to look for: monthly is pretty common. That's N equals 12. A lot of times you'll see quarterly. That's N equals 4. A lot of times you'll see problems where it's done annually. That would be N equals 1. Other ones, maybe you might see weekly. There are 52 weeks in a year. Or daily, there's 365 days in a year. So some other variations of that. So this is just plugging in. So I'd have 750 times 1 plus 0.05 divided by 12 to the 12 times 4 power. And I would start by simplifying this inside a little bit. Now these are going to be not beautiful decimals, so save your rounding until the very end. 12 times 4 is 48. I would raise that to the power. And when I multiply that, I'd get $915.67. So at the end of 4 years, you would have $915.67 in the account, and you would have earned $165.67 in interest. So this is a pretty straightforward application just to plug and chug. Now, as the number of compoundings per year increases, the balance A is going to approach a limit. So the more often you compound, the better your balance is going to be in the end, but it does reach a limit. So there's a special limit involving E. If you want another way that you can calculate the value of E is that it's the limit as x approaches infinity of 1 plus 1 over x to the x power, or the limit as x approaches infinity of x plus 1 over x to the x power. Both of those are equal to E. So if I were to take the limit as n approaches infinity of P times 1 plus R over N to the NT, I could go ahead and bring out the P. So I'd have 1 plus R over N to the NT. And if I let R over N, this is equal to 1 over N divided by R, because you would do the keep, change, flip thing and get that back. So I promise there's a reason why I'm doing that. This would be 1 plus 1 over N over R. And I could change that to be raised to the nth power raised to the t power, because if I were to multiply those, if I were to raise that power to that power, I would just multiply those. And then right here, I'm going to multiply this by R over R, but I'm going to take one of the R's and bring it outside. So this would be P times the limit as n approaches infinity of 1 plus 1 over N divided by R to the N over R power, and then that's all raised to the t power. And as n approaches infinity, n over r is definitely going to approach infinity as well, because r is a fixed small number. So if we let n over r equal to x, you can see that you do have that same limit that we were talking about earlier. It's just raised to a power. So we know that the limit of something, if we know a limit that goes to L, then the limit of that function if it's raised to the nth power goes to L to the n. So this would be P times E to the RT, or PE to the RT. So this gives us the formula A equals PE to the RT. And this is what's known as continuous compoundings. So it literally is just the limit as n approaches infinity of the number of compoundings per year formula. So just to kind of show you how the number of compoundings per year can change a problem, we have a deposit of $35,000 and it's paying an annual interest rate of 4%. So we have P equals 3,500. We have R equals 0.04, and we have T equals 5, and in this case N is going to be 4. So A would be 3,500 times 1 plus 0.04 divided by 4 to the 4 times 5. And this is 3,500 times 1.01 to the 20th power, which gives me $4,270.67. If the only thing I changed was the number of compoundings per year to 12, this would be 3,500 times 1 plus 0.04 divided by 12 to the 12 times 5 power. This one would give me $4,273.49. So you can see that it does increase a little bit. And if this was a continuous compounding, I would use the PERT formula. So this would be 3,500 times e to the 0.04 times 5. So this is e to the 0.2, which is $4,274.91. So that's as if you're constantly compounding interest on your account. So you can see that it does raise a little bit, but this is the maximum that you would get out of an account with that interest rate in that amount of time.